Exponential growth models are not always super realistic. In fact, it's pretty rare for it to be realistic because having your growth rate always be proportional to the population size, that would you go really, really, really fast. And there's got to be some type of limit to growth based on environment or conditions or whatever. And so we can't just grow without bound. And this leads us to a much more realistic model, which is called a logistic growth model. So these are where our model starts out as if it would be exponential growth, but there's something limiting that growth in some way. So that could be, maybe you've got a bacteria population, it's growing, but it's just inside of a little petri dish, and that petri dish is only so big, and there's only so much resources in that petri dish to support the bacteria, and so it has to slow down eventually. So this is the formula for a logistic growth model. Okay, Y is our population size, X is time. You can use a T there if you'd like, and R describes the rate of growth. The numbers A and B are actually pretty significant. A is the limit to growth. The limit to growth. It's also, growth. It's also sometimes called the carrying capacity. Because it's the capacity of the environment. So maybe you've got a little forest, and there's a certain number of squirrels in that forest. And those squirrels are reproducing, but there's only so many nuts. And so the squirrels can't just grow nonstop because the resources would run out. And so the carrying capacity is how many squirrels could actually survive in this forest. Okay, that's the idea of the carrying capacity, or the limit to growth. And then B helps us get the initial value. Okay, the initial size of the population. That's, of course, if we just plug 0 in for X. But if we plug 0 in here, you get e to the 0, which is 1. And so the initial size is A over 1 plus B. So that's how we can use B to interpret these formulas. Let me draw a little sketch of what these look like. So we've got some growth, and we start out at A over 1 plus B, and I'll just go ahead and mark that right here. Okay, and it starts out, we start growing, and it starts pretty fast, but then there's some limit to growth, so we've got to slow down, and we do slow down, and we start to kind of level out. Okay, in fact, we level out, and we approach an asymptote, and this asymptote is up here at A. That's the limit to growth. So this is what a logistic growth model looks like. Now, this is the logistic growth. There is also logistic decay, a little bit, quite a bit less frequent. But you just flip this around. You'd start out high and go down, and that would be where this is e to a positive Rx. And but that's pretty rare. So we're mainly going to focus on this logistic growth model. Let's look at an example. On a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this. And actually, there's a typo here. I apologize for that. This should be 4,999. So I missed a 9 in here. I'm going to go ahead and write that out. 4,999. Okay. So this is our logistic growth model. We can see here that 5,000 is the limit to growth. Okay, limit to growth. That's obviously the limit because, of course, your college campus, you can't have more people than are on campus. Okay, so the number of students infected certainly cannot get past 5,000. Okay, and our initial value is 5,000 over 1 plus 4,999. That makes sense as well because that's 1. Okay, there's 1 student that returns from vacation with this virus. So there's our model. It makes sense to us. And we'd like to know how many students are infected after 5 days. This isn't difficult. This is just plugging 5 in for T. So we've got 5,000 over 1 plus 4,999 e to the negative 0.8 times 5. All right, so we can go ahead and plug this into a calculator. So we've got, I'm going to put it over here, I've got 5,000 over 1 plus 4,999 e to the negative 0.8 times 5. Go ahead and hit enter, and we get, and of course, we're talking about number of people infected, so really it only makes sense to have whole numbers. So rounding this to the nearest whole number, we get 54. So we would expect about 54 people to be infected after 5 days. Part B, the college will cancel class when 40% or more of the students are infected. After how many days will classes be canceled? So we just want to know when we end up with 40% infection. So we take our formula, and we're going to set it equal to 40% of the population. Well, that's 0.4 times 5,000. And that's 2,000. Okay, that's 40% of the total student population. And now we're just trying to solve for t. Okay, I'm going to go ahead and multiply by this whole denominator. I don't like that I'm trying to solve for something in the denominator. So multiplying by that, I've got my 2,000 and then 1 plus 4,999. And then, e. What's that e? E to the negative 0.8 t. All right, I can divide both sides by 2,000. Okay, and I'll cancel here. 5,000 over 2,000 is 2.5. I can subtract 1 from both sides, get 1.5 equals 4,999 e to the negative 0.8 t. Now dividing by 4,999, I've now isolated my exponential. And that's nice because once you've isolated your exponential, you can just use a logarithm to get rid of that base. So if we take the natural log of both sides, okay, the natural log and the base e will cancel, and we've got our natural log of 1.5 over 4,999 equals negative 0.8 t. And finally, to solve for t, we can divide by negative 0.8. So we have natural log of 1.5 over 4,999 over negative 0.8. And that will be my t. We just need to plug this into our calculator. So let's go ahead and do that. We've got the natural log, 1.5 over 4,999 divided by negative 0.8. Hit enter, and we get t, and note that we are measuring here, t is in days. And so we get that after just a little bit more than 10 days, we've got that infection of 40% of the student population. So after about 10 days, classes would be canceled.